This chapter is one of the most important chapters in your chemistry book. It is on stoichiometry, and this is the math used to measure elements. So this is probably going to be another several-parter for video-wise, probably 4 or 5 if I had to guess. It's going to cover 40 pages in the textbook about, and stoichiometry is pretty big and has a lot of uses, and I will do some examples, so this is going to just take a large chunk of time. Alright, well the first thing the book goes over before we do any stoichiometry is unit conversion. This is a big deal in stoichiometry, so we're just going to make sure you know how to do it the simplest way. For example, if we have 2 yards and we want it in inches, we know there's 36 inches in a yard. And we just multiply the 2 by 36, and then we know that there's 72 inches, and that equals 2 yards. Well, very simple, but if you don't know how to do that, learn how to do that before you even watch this video. It's incredibly important. So, time to go. Alright, next important thing that this Barron's book covers is the metric units. Stuff you'll need to know. So standard ones for chem, you're going to use kilograms. Actually, more often than not, you'll use grams, but sometimes there are equations that are physics based and use kilograms. So make sure you use kilograms when a equation specifies the use of kilograms. Distance, they use meters. Time, seconds. Temperature is either Kelvin or Celsius. Kelvin, remember when you're using Kelvin versus Celsius, big, also important. You're going to use something called moles, which I'll talk about in a minute. Sometimes there's an E at the end. And the book mentions current, amperes, and candelas, light intensity. I've never used candelas personally, but you will use amps later for electrochemistry, but the abbreviation for that is just an A. Alright, the table also has the book also has a table like this one. It is the metric prefixes. These are also very important. I wouldn't worry too much about mega. You won't use that one too much, so I'll put an X there. But kilo uses a lot. Deci not so much, or deci I suppose. But centimeter you'd think, but not really too much. It's mostly going to be kilograms or grams, and then micro, nano, you're going to use some milli also for like liters. Pico, not so much either, but know them all. Alright, here's another quick example of unit conversion. You have 25 meters, and you know there's 100 centimeters and 1 meter because the symbol there, centi, means 100 or 100th. If you learn your prefixes anyways, 25 meters times 100 centimeters per meter. So we're just going to cancel units, right? The meters cancels out and you get 2,500 centimeters. And that is 2 meters. Or 25 meters, sorry. Which is, yeah. There you go. Unit conversion. Not super difficult, and pretty key in stoichiometry, especially when you don't have much practice with it. Alright, so here we are back at moles. Now, this 1 mole, this is going to seem like a really obscure number, and it kind of is, but it is the number that is used. So, 1 mole is equal to 6.022 times 10 to the 23rd atoms of a certain element. So if I said I had 2 moles of, or a molecule, so I could say I have 2 moles of methane, and it would be 12.044 times 10 to the 23 atoms, or 1.2044 times 10 to the 24. So scientific notation, also important, but this number right here, this guy, the weird one, You're going to need to memorize it for 1, very important. And for 2, it is called Avogadro's number. This number just shows up some, and so moles are pretty important because they let you actually do stoichiometry when you know the moles and then the molar mass. So one more slide and you'll find out what molar mass is. So molar mass is it is a number on all your tables. If I draw a diagram, this is, let's say, one element. This is hydrogen. You see the positive charge probably somewhere. See that's number 1. You probably see its electronegativity, but you're going to see this number. It'll either be in the right hand corner, or sometimes I'll see it under the element, but in this case I'll just put it under. So for hydrogen it's 1.01. This is its molar mass. Now molar mass is equal to the grams per mole of an element. So if I told you the hydrogen has a molar mass of 1, or 1.01, or about 1, you'd say that 1 mole of hydrogen weighs 1.01 grams. And remember, 1.016 1 mole is 6.022 times 10 to the 23rd atoms. So there you go. Well, a lot of you thinking, oh, hydrogen doesn't come by itself. It usually, if I get a different color here, it usually comes in pairs. There we go. Well, what's the molar mass of the hydrogen as a polyatomic ion, or not polyatomic ion, molecule? Well, there's 2 hydrogens, so 2 times the 1.01 equals 2.02. So 1 mole of hydrogen gas is going to weigh 2.02 grams. I shouldn't say weigh, it should have a mass, because mass is different from weight. Also key important, very important, don't mess that up on tests. You will probably be marked down for saying mass weighs. So that was a dumb mistake I made. Don't do what I did. But there you go, molar mass. Alright, so here's going to be a basic example of stoichiometry. Let's say I have 40 grams of, I don't know, let's say H2O. And I wanted to know how many moles. Many moles. Well, the first thing we're going to do is we're going to find the molar mass of water as a molecule. So it has 2 hydrogens, right? And we know the molar mass of hydrogen is 1.01. So then we need to add the molar mass of oxygen. Oxygen has an easy one to remember because it's 2 times its atomic number, because of, well, I don't want to go into it right now, but anyways, so you get 2.02 plus 16 equals 18.02 grams per mole. Now we can set up our equation like this. 40 grams over X mole is going to equal 18.02 grams per mole. Whoops. That guy should be up there with the 2 grams per mole. Right? Pretty easy, right? Pretty basic. You just set up the grams per mole with how many grams you have and solve for X moles. So if I do that, we get the answer to be, well, I'm sure I don't need to tell you how to solve this, but just in case, you can cross multiply, or not just do proportion. You know that that's going to equal that. So 40 moles is going to equal 18.02x. I don't even worry about units for this part. And divide each side by 18.02 to get x equals 2.2 moles. There you go. You just leave it in moles, and then now you know how many moles of H2O you have, 40 grams of water. So, not too difficult, but stoichiometry has just a multitude of uses, and you'll see more of them in this chapter. Alright, let's pretend you have 20 moles of CH4. Now, I don't know why you would go backwards in this case, because usually you're trying to go from grams to moles, because usually you're going to be in a lab and you can measure grams pretty well, but not moles. So usually you'll measure the grams of something and turn it into moles to see how effective, like what would the percentage of what your reaction worked or something. But in this example, we'll just do moles. Alright, so first we're going to look for mass. So first we're going to find the molar mass of methane. So again, we know that hydrogen has 1.01 plus carbon, which has 12.01, is going to get you 16.05 grams per mole. So now we have x grams over 20 mole equals 16.05 grams per mole. This one, pretty easy, right? You're just going to times by 20 on each side. I'll make that a dot so you don't get confused. Times 20 on each side to get 321 grams of methane. So a lot of atoms, not a lot of weight, and that's because methane is a gas. I should say not a lot of mass, and it's because methane is a gas. Alright, now we're just going to do practice one of finding a molar mass of a somewhat more complex molecule. So here we're going to do botch that. It's going to be C12H22O11. If you've done biology, you know this is sucrose. And then, well, you probably know that. But anyways, what's the molar mass? Well, we know carbon has a mass of 12.01, and there's 12 carbon atoms, so we're going to do that. We know this guy, there's 22 hydrogens, 1.01 for its molar mass. That's probably hard to read, but that is an 11. So we're going to take him and do 11 times the 16. So then we're just going to add these up to get a total molar mass of 342.34. Remember, that's what your calculator is for. Don't try to do all this in your head, because you can't afford to have any errors when finding molar mass or moles or any of this really. Otherwise your equation, your percent error, will be ridiculous. Alright, well, here's a pretty basic chemical reaction. Well, if you remember from earlier, this has an imaginary 1 in front of it, as that guy, and the oxygen and the water have 2's. Well, the chemical equation is actually telling you if you take one atom and one molecule of CH4 plus 2 molecules of oxygen, you get 1 molecule of CO2 and 2 molecules of water. Well, the same applies for moles, right? Because it'd be like multiplying the whole thing by 6.022 times 10 to the 23. So usually most people will think about this and go, oh, I have 1 mole of CH4, 2 moles of oxygen, and I get 1 mole of CO2 and 2 moles of water. Well, what if I told you you only had half a mole? How much CO2 and how much water will come out? Well, you can just divide everything by 2, right? If you have half a mole, because you can't have half a molecule, but you can have half a mole CH4 plus, that'd be 1 mole oxygen, and that's going to yield, if I switch colors, try to ignore that 2, that's from up there, I'll try to box that up there. Alright. Half a mole, right? 1 over 2 CO2 plus 1 mole water. Whoops, you don't need to write mole in, but there you go. That's just pretty basic use of, if you know how many moles you have of reactant, which are those two guys, you can tell us the products, how many moles of products you get out, assuming a complete reaction. Alright, the next thing the Barron's book talks about is concentration. So, let's even tell you what it is. They often use a big M for it. Sometimes you'll see a big C for concentration because the big M is used elsewhere. However, C is also used elsewhere. And sometimes you'll just see concentration if they don't mind writing it out. But usually, especially on the tests, you will see an M in italics for concentration. Also sometimes you'll see the actual thing written out, and what it stands for is moles per liter. So sometimes you will see that also. So if I told you you had a solution of 0.25 m or moles per liter of NaOH, which is sodium hydroxide, and I told you you had 3 liters. Well, how do you think you'd solve this? Well, pretty easy. You just set it up, 0.25 moles over 1 liter times 3 liter, which equals, that's movement now, which equals 0.75 moles. So you would say you have 0.75 moles of sodium hydroxide. Again, this is pretty important, but you probably won't see too many concentration stoichiometry problems until you start doing acid and bases. Then they'll show up a lot. But acid bases is when they show up a lot, and then when you start gravimetric analysis, I think they use it in that too, which you'll learn about later. Oh, and quick side note, they use the big M. I guess this isn't really a side note, it's a pretty big thing, but the big M stands for molarity, which is also concentration. So that's why they use the capital M. So pretty important. The other thing that you will see liters used for, and then therefore molarity, is gas. So if I told you I had 20 moles of gas in 1 liter of containment, well, you could say the gas has a concentration of 20 m, or molarity of 20. You don't see that much. You mostly actually see this for ideal gas law, but you won't learn that until your chapter about gases. So really all you need to know for stoichiometry right now, in my opinion, is how to how to find the molar mass of molecules, and how to go between molar mass and moles or mass. And yeah, I'd say that's pretty much it, but there's another 20 pages or so of this chapter, so I guess we'll keep going. Alright, well, the next thing the book covers is finding how many moles of a certain molecule in a larger molecule. So let's just do nitrogen. I'll just do the example they have here. And they have in 6.5 moles of, this can be quite the chemical or molecule, 3PO4. So for those of you who have gotten their naming down, this is ammonium phosphate. Yes, I believe, let me check the polyatomic ion table. Yep, ammonium phosphate. That's why it pays to remember. Have that memorized. You should have that memorized before probably semester 2 of your class, if you were taking the test at the end of semester 2. It's pretty important to have down. So, as you can probably guess, the 3, right, applies to the hydrogen and to the nitrogen. So we have 3 times the nitrogen, so you're just going to do 3 times the 6.5 originally, and you get 19.5 moles of nitrogen that are inside of 6.5 moles of ammonium phosphate. So to solve these, if they give you this like ammonium phosphate in words, I would write down the chemical, this form of the chemical, and then just multiply. It's pretty easy, pretty straightforward. Alright, so another thing that might happen is I might tell you I have 3 grams of, let's just do 1 gram. We'll just make it 1 gram. I have 1 gram of this, this is propane here, but again, naming, you won't have that until you do organic chemistry. But if I have 1 gram of C3H8, how many grams of CO2 will I get? Well, first thing you're going to want to do is turn the grams into moles. So if I'm going to do multiple steps at once, we're going to get 1 gram over X moles equals 3 times 12.01. It's hard to read. Plus 8 times 1.01 equals, gives you 44.11. So then we're going to just solve for moles. So multiply by x by h by 44.11 to give you 1 over 44.11 moles, or 0.022, or 23 actually. So pretty small number. If you're doing this on your calculator, I'd leave the answer there, not clear it, and then use the answer key to keep doing your math, because you want this to be exact as possible. Well, from the equation, we know there's 3 times as much CO2 as there is propane at the start of it, because there's the imaginary 1 there. So multiply this number by 3 to get 0.068 moles of CO2. Well, now we just need to turn that back into grams. Well, we know CO2 is going to have 0.068 moles, x grams, and it's going to equal 12.01 plus 2 times 16, which is 32, giving it a molar mass of 44.01. So now we just solve for x. Times each side by 0.068 to give you 2.99 grams of CO2. So there you have it. And because as you can see, because propane and CO2 actually have roughly the same molar mass, the ratio of grams actually turned out pretty close to the ratio of moles, but that's not something that happens a lot. So don't try to just multiply that by 3 to get there. It's not going to work. You need to turn everything into moles and then back into grams. This actually turned out to be much quicker than I thought it was going to be. I think I can get this all in one video now. The Barron's book just has a ton of examples, and they all take up a lot of space. So if you do need more help, the Barron's book is the place to go. It just has looks like 6 or 7 examples for each of the subtopics. So lots of practice work. But here we're gonna start doing something called limiting. If I can write limiting. And this is labeled limiting reactant, but I always learned as limiting reagent. They're pretty much the same, so I'll just put reactant there too. It's just the basic idea of it is let's say you have the equation that we had from last problem, just see it, plus 5O2 makes 3CO2 plus 4H2O. Well, if we look at this, we see that this takes up a lot more oxygen than it does propane, right? Because 5 is a lot bigger than 1. Well, that's pretty common sense, right? Well, what if you have less oxygen than you do propane? Well, then the reactions, you're not going to use all the propane, are you? You're going to run out of oxygen first, so the reaction will just stop. So the idea of the limiting reagent reactions is that first you find out which of the two reactants will run out. So run out, and then you will more than likely have to find out like how much of each product actually was made after or using the limiting reagent. So that is generally what the limiting reagents are about. So without further ado, alright, well, let's just use the equation from before, just because I still have that in my brain. So if I tell you you have 10 grams of C3H8 and 10 grams of oxygen, first you're going to find limiting reactant. So I'm just going to do that. X is usually short for just the action, so you might see reaction written as RXN. Anyways, so the first thing we're going to do is turn propane into moles, right? So I'll just put an arrow there. And again, we know 36.03 plus 8.08. I'm just going fast here because by now you should have some practice with turning the molecules into their molar mass. So yeah, so that's going to have the molar mass of 44.11, and we know 10 grams over X moles equals 44.11. Multiply each side by X, divide each side by 10, and you will get 4.41 moles C3H8, I think. Yeah. Alright, so now we're going to go to the oxygen. I'll do that in a different color. Well, oxygen is just 2 oxygen, so we know it has a molar mass of 32. This problem will probably take up 2 slides just because space is running out already, but 32, and then we know 10 grams over X mole makes 32. Well, I'm going to multiply each side by X again, divide each side by 10 to get moles equal 3.2 mole of O2. Well, let's just talk about this answer for a second. We know we have 3.2 mole of O2. We have 4.41 of, I should put 20, be a good example, because the rules using places. Yeah, anyways, because we know 4.41 is greater than 3.2, so the limiting reagent here is going to be oxygen. Well, that happens to work out for this problem. But the other thing you have to keep in mind for most problems, if I can get a new color, is the numbers in front. Well, that one has an imaginary 1. Well, the mole of oxygen rate, well, in fact, you're going to have to watch out for it in this problem too, because the mole of oxygen to propane is that's consumed in this reaction is 5 to 1. Well, the important thing about this is that to use the 4.41, all of that, we'd have to have 5 times as many moles. So we'd have to have something like 21.05 moles of oxygen. Well, we don't have that many. Well, let's see how many we do have. We have 3.2, right? So we can use the 3.2O2, but we can't use 3.2 of the propane because that's not the ratio. It's a 5-to-1 ratio. So we're going to have 3.2. So we're going to mess that up there. 3.2 over 5 of C. You know what? Just wait a second. I'll put this on the next slide. So picking up where I left off, we're going to have, oops, if I can draw, 3.2 over 5 of C3H8, and then plus 3.2O2. Now, you never write an equation with these decimals and fractions, but just to think about what's being produced is the easiest way to do it. Well, if you remember from the equation before, we have the propane, right, C3H8 plus 5O2 makes 3CO2 plus 4H2O. So that means the CO2 to C3H8 ratio is 3-to-1, right? Because that has a 3 and that has a 1. So we're going to have 9.6. If you don't know where I'm getting that number, it's the 3 from there times that number there over 5 of CO2. And we're going to have the 4. Ugh, that was an ugly H then. 4H2O, right? We're going to have that 4 times that number also. So plus 12.8 over 5 H2O. So in this reaction, the limiting reagent is oxygen. That's the one we have the least of. And we produce 9.6 over 5, which is 1.92 moles of CO2. And 12.8 over 5, which is 2.56 moles of H2O. So turn those into moles, and then from there is one more easy step to turn those into grams if you're looking for the mass of reactants produced. So there you have it. That's a limiting reagent example. So really fast, one more tidbit is that if we turn these two answers back into grams, it is something called the theoretical yield, which is the maximum amount of product formed in a reaction based on the amounts of reactants used. So yeah, so that's what you'd be solving for, would be which is the limiting reagent, that guy, and then what is the theoretical yield. Alright, so this is well, it's hard to draw on this thing, but this is supposed to be an example of titration. So titration is a process used to it's usually define the pH of an acid or the concentration of an acid, which is very related to the pH. So what happens is you have an unknown concentration down here, so question mark, and up here you have the neutralizing agent that you know what it is. So usually if this was an acid, let's say this was sulfuric acid H3SO4, I think, then this guy, you'd probably use something like a strong base like sodium hydroxide. So what happens is you put a little something called an indicator. So it'll just be a drop or a few drops of a solution like something called bromethymol blue, or you'll use litmus paper, but not usually for titrations. And what happens is you turn this knob here and it lets some of the base out in this case, but you can also use an acid in here in this, and then to solve the concentration of a base there. So anyways, so turn the knob, you let drops out, and all along here are measurements. So maybe here there's 50 mil in there. If it's filled, maybe here there's 10. So you can see how much of the solution you're adding, and at a certain point these drops will change the pH of the solution, because the acid or the base will begin to neutralize the solution that's in the beaker. And so at a certain point, now this is what the indicator is for, the indicator will change colors to let you know that the well, usually what happens is, let's take bromothiamyl blue for example. It is clear when it's an acid, if I remember correctly, but it turns blue when the solution becomes basic. So if we have H3SO4 in here, and H3SO4 has a high pH, probably close to 1 or 2, and sodium hydroxide is going to have I should say a low pH, 1 or 2. If you don't know your pH scale, it's 1 to 6 is usually acidic. Actually 6 is kind of on the edge, because then you get, so I'll say 1 to 5, then you get 6 and 7, sometimes 8, they're considered neutral, and then 9 to 14 is basic. So the indicator is a special chemical that will in bromothiamyl blue's case, it's clear when it's acidic, but so that's why I use gray, because that'd be clear, but when it turns basic it turns blue. So as you're adding your base, if I get a really blue color here, as you add your base, the pH will get to 7, and then you'll add a little more, and then it'll turn to like 9, and then this will all of a sudden, very suddenly, turn blue. So as your instructor will explain, when you're doing the experiment, you have to constantly be swirling this glass to keep the concentration equal throughout the whole solution. And it's kind of a complex concept, but the whole point is that you can use a known concentration plus a indicator to discover unknown concentration. So that is the goal of titration. Works with acids and bases. I know a lot of stuff to cover. You might want to watch that thing again. It's really important when you do acids and bases, and it's got some stoichiometry in it that we're going to do next slide. Really fast, I'd like to amend an error. It is H2SO4. That is my mistake. I was thinking of hydrophosphoric acid, which is H3PO4, H3PO4. Hydrosulfuric acid, or I don't want to get into names right now. It's just going to confuse me. It's going to confuse you, but this is H2SO4, not H3SO4. Alright, so here is a lot of writing, which probably doesn't leave me with too much room to do the math, but I'll try to fit it on this one slide. So we have an unknown concentration of sulfuric acid in half a liter of solution, and what happens is, through titrating, we have the sodium hydroxide in the little in the titration apparatus, and so we add and we know actually I shouldn't really give you that number. We'd say let's forget about 4 moles for a minute. Let's say we add let's say I add 0.5 liter of 2, just changing all the numbers now, of 2 moles per liter concentration. Well, first how much sodium hydroxide did I add? 2 moles per liter times 1 over 2 liters makes 1 mole added, right? Well, now we need to know how much and what the concentration or how many moles of the H2SO4 there are. Well, the first thing you should know about this reaction is it's going to be kind of tricky, because in this case what's happening is the because there's 2 hydrogens in sulfuric acid, you get 2, if I can write, I get 2H plus the 1 OH from the sodium hydroxide, right? Well, here's where the problem starts, right? Well, we have 2 hydrogens there, and there's only 1 in sodium hydroxide. Well, that means there needs to be 2 of that too, right? Well, that means we need twice as much sodium hydroxide to neutralize, we need 2 times as much sodium hydroxide as we have sulfuric acid to neutralize the solution. So, and then plus the SO4, 2 minus plus the Na, we need 2 of those to neutralize. So then, this is just a neutralization reaction. You don't really need to understand what's happening now, but there's that guy is called a hydronium ion, and that guy is called a hydroxide ion, and that's what determines the acidity or the basicness of a solution. So those 2 combine to make water, HOH, as you'll see it in renin acid-base reactions, and then these 2 will make a salt. In this case, it's going to be sodium sulfate. Alright, well, all we know at this point is that it took us half a liter of 2 moles per liter, so that means we have 1 mole of sodium hydroxide. Well, we know that there has to be a 2-to-1 ratio, right? So it means we have half as much H2SO4, so 1 over 2 makes 1/2, and if I change colors, this is going to be the 1/2 is for that, 1 for that. So we have half a mole of H2SO4 and half a liter. So I know, again, it's kind of scrunched in, but we're pretty much done. 1/2 over 1/2 mole over liter. We get molarity of 1 for the SO4. So there you have it. That's how you find the concentration with a titration. Yeah. So again, this is a neutralization reaction. You don't really need to understand what happens right now, except all you need to know is that you need an equal amount of OH as you have H plus ions. So in this case, since there is double the H plus per molecule of H2SO4, we needed twice as much NaOH, or sodium hydroxide, to neutralize it. There you have it. Pretty messy, because I had to fit it all on one slide, and a lot of new concepts between neutralization here and more ratios, but not horrible. Alright, the final, or one of the final, pretty much the final step in this is, or not step, I should say, use for stoichiometry that we're going to cover in this chapter is percent composition. So this lets you see how much of each element there is in 100 grams of a substance. So let's pick a molecule. I'll do lithium fluoride. Why not? So that is LiF, for those of you who still don't have the naming down. And so what we're going to do is we're going to find out how much of how much lithium is in lithium fluoride. So here, I'll put that up here so we can remember that. So we have 100 grams LiF. That means we have, well, let's add up the molar masses. Let's find the molar mass of lithium fluoride first. So the molar mass of fluoride, or fluorine, 19, plus the molar mass of lithium, which is 6.94. So we have 25.94 divided by x moles equals 25.94. Now you could probably estimate it's about 4 moles, but let's find out exactly how much. So we're going to multiply each side by x and divide each side by 25. So 100 divided by 25.94 is 3.85. And we'll do 86. It's 855. Alright, now I'm going to switch colors. Alright, so now we have 3.86 moles of lithium fluoride. That means we have 3.86 moles of fluorine. So now we need to find out how much that weighs. So we got x grams over 3.86 moles equals, remember the fluorine is 19, so just multiply each side by 3.86 times, messed up there, times 19, and then we get the grams of fluorine is 73.24. So, or 25 actually, it's 245. Alright, so from this, since we start with 100 grams, and there's 73.25 grams of lithium, or of fluorine and lithium fluoride, we can determine that there's that much of it in there, but the way you would conclude this is you would say there's lithium fluoride is 73.25% fluorine by mass, and do 100 minus the answer, you get it is 26.75% lithium by mass. So there you go. This is important skill because later they will just give you a empirical formula, and you'll have to know, you'll have to use stoichiometry to find out what the actual molecular formula is. I'll go over empirical formulas in the next slide if you do not know what that is. Well, let's take an example. So let's say I have the molecule C2H8. Well, this is ethane. When you learn your organic chemistry, I know I make a lot of references to that. That's because the naming comes up a lot, and Barron's book isn't there yet, so don't worry about the names. Alright, well, this is the molecular formula. Well, you might notice that both the 2 and the 8, the little subtext of each element, they're both divisible by 2. So if I say green is molecular, and then so I use pink because I wrote empirical in pink, you divide each one by 2 and you get CH4. Well, this is methane, but it's also the empirical formula. So it's the molecular formula for methane, but it's also the empirical formula for ethane, and propane, and butane, and pentane, hexane, and so on. What the empirical formulas are really just the elements in the molecular formula, which would be just the normal one, but then divide it out. So it's like reducing a fraction. But unlike reducing a fraction, empirical formulas are just not as useful. But they do show up sometimes, and that's when the percent composition by mass, the thing that we just did, that's when that comes in handy. Because if I told, well, it helps you figure out molecular formulas more. So the example that the book gives you, they might tell you that you have 4 grams of calcium and 7.1 grams of chlorine. So what you need to do is, like we did before, determine, well, here actually we already have the grams, but if we do 4 divided by 4 plus 7.1, we get the percent composition of calcium. So calcium is going to be 4 divided by 11.1, which is 36%. That's percentage by mass. Well, you can also turn these grams into moles. I'll do that on a new slide right now. So the way the book does it is they take the 4 grams and they divide it by X mole to get the molar mass of calcium, which, when you look on your chart, is 40.08. I'll just leave it as 40 to make this easier. So moles obviously is going to be 0.1 mole calcium. Well, then we take the 7.1 grams of chlorine. I'll do this in a different color actually. Let me erase. Alright. 7.1 grams chlorine over Y moles, and that is going to equal the chlorine one, which is 35.5. So obviously we have 0.2. I don't know why that blue 7.1 came back. I tried to kill it before. Not important. Just ignore it for now if you can. Of chlorine. So now, if you're 0.1, you're 0.2, you can see that there's 2 times as much chlorine. So your empirical formula, I'll do this in red so it's different. It's going to have twice as much calcium as you have chlorine, or twice as much chlorine as you have calcium. And since it's an empirical formula, you just want things in the lowest whole numbers as divisible by. So you just say the empirical formula is calcium chloride, or CaCl2. So now the book talks about molecular formulas. Well, as you probably know, they're just the regular formulas with everything to their normal numbers. Well, if we have the empirical formula CH2O, well, if we have the molar mass of the whole molecular formula, we can determine the, well, in this case, the molar mass of the whole thing is going to be 180 grams per mole. Well, the molar mass of the empirical, that guy, is 12 plus 2 plus 16. Just going to use the round numbers instead of the decimals in this, just because either way it's going to come out as a small whole number or very close to it, and you just round to the closest number. It's going to be pretty darn close. Well, in this case it's 30, right? Well, 180 divided by 30 is 6. So you just times the empirical formula, all the little subscripts and the imaginary ones there and there. I'll even put them in. You just multiply them by 6. So the real thing, if I change color here, will be C. 1 times 6 is 6. H, 2 times 6 is 12. And O, 6 times 1 is 6. You get C6H12O6. So there you go. That's how you turn an empirical formula into the molecular formula if you're given the molar mass, or can find out the molar mass of the real molecule. Alright, last slide everyone. Good job sticking with it. Well, this is just pretty much a wrap-up slide where I'm just going to show you it has a few equations here in the Barron's book. I'm not sure why they put them here, but I will show you some of the handy ones. Most of these, like this one, which is going to tell you the moles is equal to grams over molar mass. You can find that out pretty easily just by shuffling the normal equation that we have down, which is grams over moles equals molar mass. But if you just would prefer to memorize another equation, there it is for you. The next one, which is also pretty straightforward, the amount of moles is equal to the molarity times the liters in the solution. Well, this is pretty obvious because if you remember, M is short for mole over liter. So another pretty easy one. This one is less pretty and also much less commonly used, and you won't even see it till you do gases, but it's in the book, so I'll just put it down in case your teacher wants you to know it now. I doubt they will though, but the moles is going to be equal to liters of gas. Remember, of gas, not of liquids or solids, only of gas. But divided by 22.4. Now, 22.4 seems like a random number. It has to do with standard ambient temperature, SATP, I think, or it's STP. It's one of those two. There's a couple standard temperatures that you use for gas and standard environmental. It's one of those two, but that's where that comes from. So doesn't seem so random. And the last one is the moles is equal to, and this is pretty easy also if you remember from before. We even pretty much covered it. Really, we actually did. Is equal to the numbers of molecules divided by the Avogadro's number, which is, boom, to the 23rd. So there you have it. Those are the 4 basic equations that you should be taking away from this long, lengthy video, along with the skills like percent by composition and titration. A lot of material, but stick with it. But yeah, that's that. Great job.